Okay, we'll finish up now with an example, several examples of how to draw Lewis structures. And the rest of these examples will be primarily for covalent compounds. So let's take a look at some covalent compounds. Here's an example of two chlorine atoms that come together to form a chlorine molecule. And what happens here is the two electrons that are shown between the two symbols ClCl are shared and form a single bond between the two chlorine atoms. And so this one is an example of a single bond, covalent bond, and because these are two identical atoms, the electronegativity is the same, so it is totally nonpolar. There's no difference in what side shares more of the electrons. Now this can also be shown in a different way, where the pair of bonding electrons is shown as a dash, so that's the bond, and then the remainder of the electrons are distributed around the outside of the two chlorine atoms. And so you can show it as on the right upper part that way, or you can show it in the right lower part that way. And each dash represents two electrons. Remember, you always have to have the same number of electrons that you started with. And if you look, you have 7 around each chlorine atom, so there's a total of 14. If you count the electrons in the right upper corner, you'll see that there are 14 there. There are 12 represented in the lower right, but the dash is the other 2 electrons representing the other ones. Now, hydrogen has 1 electron and in the valence, and so the 1 electron from each hydrogen is shared, and you end up with a bond, and there aren't any electrons left, so there are no dots to show. Here's some other examples. On the left, you have the compound carbon tetrachloride. Carbon, if you look on your periodic table, you'll find that carbon has 4 valence electrons. So each of the valence electrons for the carbon combines with or is shared with 1 valence electron from each chlorine, so that you end up with 4 pairs of shared electrons between 5 atoms. And it's shown again on the next door with 4 dashes. Similarly, silicon has 4 valence electrons, and hydrogen comes in and shares an electron with those 4, and you have the same situation, but because hydrogen doesn't have any other electrons, there are no dots around the outside. Whereas with carbon tetrachloride, each chlorine has a total of 7 valence electrons, so it shares 1 as the pair of shared electrons, but it has 6 left over that have to be represented around the outside of each of those chlorines. And see, every one of these atoms in both of these situations, except for hydrogen, because it's a unique situation, has 8 electrons when it's done bonding. So the carbon has 8. You can see them if you look at the one on the far left. Each chlorine has 8, as it shares that 1 pair with each from the carbon. And the silicon on the right here has 8. Now hydrogen only has 2, but it's one of the few exceptions to the rule of octet because it's a very simple small atom. Now let's take a look at some rules about, first of all, let me say that this is other examples of compounds that form by sharing. Ammonia, and if you look on the periodic tables, in the 5, so it has 5 valence electrons. It shares 1 of its electrons with each of 3 different hydrogens. So each dash here represents a pair. So if you take 2, 4, 6, and then the 2 that are shown at the top there, nitrogen has its rule of octet satisfied. Similarly with water, and similarly with hydrogen fluoride. Formalin or formaldehyde forms a double bond. And double bonds can be shown in two ways. And it's also shown here with ethylene. You see the carbon, and then there are two pairs of electrons that are between the C and the O. That represents a double bond, which is shown as two dashes on the right. So you have a pair of shared electrons between a carbon and a hydrogen, a pair of shared electrons between the other carbon and hydrogen, and then two pairs of shared electrons between the carbon and the oxygen. And the oxygen then has two or four leftover electrons that have to be represented. If you look at ethylene, the carbons actually share two pairs of electrons, and then the remainder of the electrons are shared with hydrogen atoms. So how do we go about writing Lewis structures? First of all, I want to point out at the top here an example of triple bonds. And notice there are three pairs between the C and the O in carbon monoxide. So there is a triple bond between the carbon and the oxygen. And then the remaining two electrons in the carbon and the remaining two electrons in the oxygen are left on the outside. Similarly, cyanide, and remember, cyanide ion has an extra electron that makes it negatively charged, and that's what allows it to fulfill the rule of octet. Otherwise, because nitrogen only has 5 electrons, it would be short one. And so it forms a triple bond. The one extra electron that makes it an ion comes in and pairs up with the remaining electron left over on the right side of the nitrogen, and then you have a pair on the left side of the carbon. So these are examples of Lewis structures for single, double, and triple bonds. So let's look very carefully at how one would go about writing these Lewis structures in a systematic fashion if you don't just know the answer. So first of all, you determine the total number of valence electrons. For cations, subtract 1 for each positive charge, and for anions, add 1 for each negative charge. So for example, if we were looking at the carbon and the oxygen up here, before they come together, oxygen has 6 valence electrons and carbon has 4. So the total is 10. So you have 10 valence electrons. So you draw a skeleton structure arranging the atoms around a single central atom and connect each central atom with a single bond. Well, in the case of carbon monoxide, there's no real central atom. The idea of a central atom occurs when you have more than 2 atoms involved. But so you would draw the C and the O next to each other, and you would put one single dash or one single pair of shared electrons to show them being connected. And that dash represents 2 of the 10 total electrons that you have. You can distribute the remaining electrons as pairs on the terminal atoms. So if you take the remaining 8 electrons, you could put 4 electrons around around the oxygen and 4 electrons around the carbon. But in that case, you'd have 6 electrons in each atom, which doesn't fulfill the rule of octet. So it's not going to be very happy. So that's where this next rule is similar, since you don't have any central atom. These two are just together. So you start out, you still have you have 4 electrons around the carbon with the dash holding them together, so that's 6, and 4 electrons around the oxygen with the dash, so that's 6. And this is when you take into account forming double or triple bonds. So if you take and put 2 dashes between the oxygen and the carbon, which means you have to take 2 electrons away from one of the 2 elements, you end up with 2, let's say we take 2 electrons from the oxygen, so it only has 2 left on the outside. and it has 2 pairs from the bonding, so it still only has 6. And then the carbon has 4 on the outside, and the 2 pairs make, so it's now fulfilled. But because the oxygen is still not fulfilled, you actually have to take a 3rd pair from the outside of the carbon, and that way you end up with the structure as it's shown on the slide. And this is the only way you can fulfill or maximize the octet. So these are the rules, and we'll go through these rules again more carefully in the next couple of slides. So we're going to draw the Lewis structure for these 4 compounds. Silicane or silicon hydride, the carbonate, bicarbonate ion, the nitrite ion, and oxygen difluoride. First of all, you arrange the atoms with a central atom. Well, first of all, you would count, for each of these, you would count the number of valence electrons. For the first one, silicon has 4 and each hydrogen has 1, so you have a total of 8. In the second one, the hydrogen has 1, the carbon has 4, so that's 5, and each oxygen has 6. So 5 plus 12 is 17, and it's negatively charged, so that means there's a total of 18 valence electrons. For nitrogen oxide, you have 5 for the nitrogen, 6 for the oxygen, so that's 11, minus 1 for the plus sign, so that's 10. And then for this oxygen difluoride, each fluorine has 7, so that's 14, plus 6 is 20. So let's do what it says and arrange the atoms with a central atom, and also attach these atoms with single bonds. And this is the way it would look. So you use the silicon as the central atom, and you could argue about which atom should be the central atom with the second one, but I will tell you that in most cases, the carbon or silicon or nitrogen is commonly the central atom. The third one doesn't have a central atom because there's only 2 of them. And then lastly, usually if you have 2 of something and 1 of something else, you put the 1 in the middle and put the 2 on the outside. So the oxygen is in the middle and the 2 fluorines are on the outside. So in the case of the silicon tetrahydride, you had 8 valence electrons to start out, and you've already used them all up. So you really don't have to do anything else. In the case of the second one, you'll remember we said there was 5 plus 12, 17, plus 1 is 18. You've only used 6 of those 18 so far, so you have 12 to use next. So that's what we're going to look at next. So you're distributing the remaining electrons as pairs around terminal atoms. As I said, with silicon hydride, you don't have to do that because you've already used them up. We had, let's count them again, we had 1 plus 4 with carbon, we're talking about the second one here now. 1 plus 4 is 5, plus 6 times 2 is 12, is 17, plus 1 is 18, minus 6 is 12, and we're going to put 6 around the outside of each of the oxygens. So right now this looks pretty good. Now the one problem is this carbon here doesn't have 8 electrons. It doesn't fulfill the rule of octet. It only has 6 electrons because it has the 3 bonds. So we're going to have to do something about that. Nitrogen and oxygen, we combine those 2 together. We have 6 and 5 is 11, minus 1 for the plus sign is 10, minus 2 for the dash is 8, so we've put 4 around the outside of each of these. Again, neither of these atoms fulfills the rule of octet. And then the last one here, we had a total of 14 plus 6 is 20, minus 4 is 16. We only have 12 around the outside here. We probably ought to do what it says next, which is to leave any leftover electrons, which in this last one, the only one that had leftover electrons was the F2O. And we had, after we put all this together with 12 plus 4 or 6, we had 4 left over. So we're going to put those 4 on the oxygen. So now this one is fulfilled. So we've fulfilled 2 of them now. If we go back to this diagram, the one on the very left, the silicon hydride, it's okay. And now with the putting those electrons around the oxygen difluoride is okay. Remember, the 2 in the middle here are not okay. So we have, by putting those electrons on the oxygen, we fulfilled the rule of octet for all 3 of the atoms. And then the last thing we have to do is to use multiple bonds to maximize the octet, and that's what we do here. Remember, the carbon in the middle here only had 6, so we take a pair from one of the 2 oxygens and we make a double bond out of it. And by doing that, we now fulfill the carbon as well as the other atoms involved. Similarly, neither of these were fulfilled as originally, but if we take a pair from either, you can take the pair from either one. If you take a pair and put it in the middle, you see that it fulfills. Well, actually it doesn't yet, because the nitrogen is fulfilled, but the oxygen is not. So you're actually going to have to actually put another one in there, take one from the nitrogen, and that's the way you fulfill it. And so now we've fulfilled the rule of octet for all 4 of these. Now I would strongly recommend that you go through these last few slides and make sure you understand, and we will do some of these in class as well for practice.